All right, this is 16.4b. We're going to continue Green's theorem. We're going to be talking about Green's theorem in reverse. Now I want to make sure you understand that that does not mean that we're going to be able to transverse our line integral clockwise. It doesn't mean that. We actually still have to make sure it goes counterclockwise in order to use Green's theorem. The idea is that what I was giving you before was a way to do the line integral of p dx plus q dy as a double integral, and it made it easier. Well, now we're actually going to take the idea and say, well, wait a minute, maybe if we don't like the way we have to do this messy double integral, we can go backwards and actually figure out a way to do the line integral p dx plus q dy much easier. So that's what we're going to look at here. So just a quick reminder, Green's theorem, you've got some kind of a closed figure, which again we have to transverse this thing counterclockwise. So something like that. And it's going to be over some kind of a region D. So what's inside there is your domain. And what's on the outside here, this is basically your C on the outside. All right, so in order for us to do this thing in reverse, again, it doesn't mean we're transversing it backwards. What it means is we're going to take the idea of the line integral of p dx plus q dy. It's tended to be some kind of a messy line integral, and it's just much easier to do a lot of times if you can put it as the double integral over d of dq dx minus dp dy. It just makes it easier. Well, sometimes those are actually going to be a little bit more challenging to do, and it's going to be easier to go backwards into the actual line integral and to do that instead. So that's what we're going to look at. There's a couple of, there's one specific special case that's going to make this a little bit easier for us to do. And that's what we're going to focus on here. So our special case is the case where dq dx minus dp dy is equal to 1. Now if you think about that, if dq dx minus dp dy is this piece right here is 1, then what you're going to get, if you haven't already figured it out, is that our line integral over C of p dx plus q dy is going to equal the double integral over our domain of just 1 dA. But if you remember that the double integral of 1 is just the area of d. Because if you think about it, you would have the first integral length, the second integral width, and then your 1 would be like a height of 1. So then you would really just have the area of something which is pretty much flat. So you would have the area of d. That's what we're getting there. So when does this kind of thing happen? That's one of the questions. Well, there's an infinite number of ways that this could happen. There's a whole bunch of ways that we could write our integral of p dx plus q dy so that we would get 1 on the inside there. We're going to focus on 3 specific ways. So let's take a look at the specific ways that this can happen that we're going to do it. Again, there's an infinite number of them, but we're only going to focus on a few of them. Get rid of this little dot there. There we go. All right, number 1. I'm trying to leave this right at the top of the screen so you can still kind of see our Green's theorem up there. If we let q equal x, well, if you let q equal x, then p would have to be 0. Well, why is that? Let's take a look. So if we have the double integral, I'm sorry, not the double integral, the line integral of x dy, that's what that would leave us with. If q is x, which would be right here, and if p is 0, that goes away. Well, dy in this case wouldn't matter, and dx in this case wouldn't matter. So q dy I'm not sure if I just said that right, so I apologize. dy does matter because it's in here. It's dx that doesn't matter, and the p is 0, so it goes away. So if we were to take the derivative here, dq dx, remembering that what we have right here is the q part with respect to x, you would just get 1. So that does work. dq dx is 1, dp dy would be 0. So you would get 1 minus 0, that's 1. This would give us the area of D. So here, let me just illustrate that real quick. So from this, dq dx is 1, dp dy, because there is no p and y, is 0. So you would get 1 minus 0, which is 1. Hopefully that makes sense. So your dq dx minus dp dy would be 1. Okay, second case. Well, what if we want to include the p instead? Well, then p would actually have to equal the negative y, because again, you're going to be subtracting dp dy, so you would want to make sure you're subtracting a negative one when you take the derivative. So which means that q, of course, would have to be 0, and then you would have the line integral over c of negative y dx. And of course, that is also going to give you the area of D. And again, I'll illustrate real quick here for you that dq dx, well, there is no q, so that's 0. dp dy is going to be negative 1, so you would get 0 minus negative 1, that is 1. Okay, and that's exactly what we're looking for. Okay, so those are two of the very basic cases. Then you're going to have a third case, which really could be any fractional sum that's going to get you to 1. We're going to focus specifically on what if q is 1/2 x and p is negative 1/2 y. Well, then what you would get is you would get the integral, your line integral, make that a better circle, there you go, of 1/2 x dy minus 1/2 y dx. And what you can do is you can factor out the 1/2, and this is usually the way it'll be seen. Oops, factor out the 1/2, and then you'll have x dy minus y dx. And again, in green here, I'll show you that this works out. So dq dx, the derivative of q with respect to x is 1. dp dy is negative 1, so you get 1 minus negative 1, which of course is 2, but then don't forget to multiply it by that half out in the front, and you end up with 1. So that also is going to work. Now again, this could be any combination. Q could be, a fourth of x, and p would be negative 3/4 of x. Or q could be a third of x, and p could be negative 2/3 of x. As long as what you get when you do the subtraction of those fractions adds up to 1, it will be okay. All right, so let's look at a couple of examples here to show just why this actually works, and to show that doing Green's theorem in reverse actually does give us what we're looking for. So the first example is we're going to check the cases that we had before. We're going to check all 3 of them. If we have a circle of radius 5, in order to do that, we're going to need to parameterize it. So first of all, we have a circle, radius 5. We're going to do all 3 cases. We're going to do case A, where we have the line integral of x dy. That was one of them. We're going to do the case where we have the line integral of negative y dx. And then we're going to do the case, I'm not going to write it in until I figure out how much room I need there, but we're going to do the case of the 1/2 of the line integral of x dy minus y dx. So in order to do this, we are going to need to parameterize this. Parameterize it. Well, we are talking about a circle, so it makes sense, because our circle's radius here is 5, to parameterize this in terms of polar. And if you remember, in polar, x is r cosine theta, y is r sine theta. Well, r here is 5 because it's a radius of 5. So x is going to be 5 cosine, you can use theta, I'm going to use t in this case, of t. And then y is 5 sine t. So we've gone ahead and parameterized this thing into polar, which should make it a little bit easier. So our line integral, let's go ahead and do these in green. Our line integral, so this is going to be an entire circle. It's going to go from 0 to 2 pi. It's going to go all the way around the circle. Because really what we want is if we start this thing when t is 0, that's going to be right here, because cosine of 0 is 1, so 1 times 5 is 5. And sine of 0 is 0, so that gives me no height, so that's right there. And then if t is pi halves, cosine is 1. I'm sorry, cosine is 0, so there's no x value, and sine is 1, so that's going to put us up here. So we are transversing this thing in the correct direction. That is actually important to make sure that that's the case, that you're going around it in the correct direction. So 0 to 2 pi looks right there. All right, so the first one, x. X is 5 cosine t. dy, so we need to take the derivative of y. The derivative of y is going to be 5 cosine t dt. Okay, I didn't write that down. Probably should write that down somewhere. Don't want to run into my other problems there, but anyway, hopefully you should be able to take dx and dy pretty easily. Okay, so let's go ahead and finish this one out. So we're going to have 25 on the outside, integral from 0 to 2 pi of cosine squared t dt. We're going to have to use the reduction formula for cosine squared. Probably just be the easiest here to do it that way. So we're going to have 25 integral 0 to 2 pi. The reduction formula for this one is 1/2 1 plus cosine of 2t dt. I can pull that 1/2 out to the front and take antiderivative. So we're going to get 25 halves. Antiderivative of 1 will just be t. Antiderivative of cosine 2t, remember, is going to be 1/2 sine of 2t. And we'll evaluate that from 0 to 2 pi. So we'll get 25 halves times. If I plug in 2 pi, now I get 2 pi plus 1/2 sine of 4 pi, but that's 0. Minus, if I plug in 0, I just get 0 plus 0. So we're going to get 2 pi times 25 halves, which is going to give us 25 pi. All right, now if we do everything correctly, all of the other forms should be exactly the same. So let's go back up here and start this one. Again, we'll just go ahead and keep this in green. So let's see here. We're still going to have an integral. We're still going to have here an integral from 0 to 2 pi. Now this time negative y is going to be negative 5 sine t. dx is going to be the derivative of x, which is going to be negative 5 sine t dt. So let's see, we're going to get 25 integral from 0 to 2 pi of sine squared t dt. Once again, we'll have to use a reduction formula. So that'll be, in this case, it's 1/2 1 minus cosine of 2t this time. So once again, we can pull that 1/2 out to the front. And then we can take antiderivatives, which will give us t, and then this will just be minus 1/2 sine of 2t from 0 to 2 pi. So plugging in 2 pi, once again we get 25 halves times, what is that, 2 pi minus 0, and then minus 0 minus 0. So it still works out to be 25 halves times 2 pi, which is 25 pi. So far, so good. And the last one we want to check, we'll call this letter C. think I'll have just enough room on the page here, so hopefully you will too. Letter C, we want to check 1/2 line integral over C of x dy minus y dx. Okay, and you should have it on your pager. I'm not going to keep scrolling up and down, but 1/2, once again, integral will go from 0 to 2 pi. Let's see, x was 5 cosine of t. dy was also 5 cosine of t dt. Minus y was 5 sine of t. And dx was negative 5 sine of t dt. And I can pull the dt's off to the right now, so I'm going to have 1/2 integral from 0 to 2 pi of, let's see, 25 cosine squared t. The minus minus becomes plus 25 sine squared t dt. And I can pull the 25 out to the front. This is wonderful, because then I'm going to get the integral of cosine squared plus sine squared, which is just 1 dt. So taking the antiderivative, we get 25/2 t from 0 to 2 pi. Plugging in 2 pi, you get 25 pi. Plugging in 0, you get nothing. So there you have it. All three of these work. All right, our second example here is actually a pretty short one, but I think it's a pretty cool example. We're going to find the area of an ellipse. If you happen to already know what that is, then this won't come as any surprise at the end. But we're going to find the area of an ellipse using Green's theorem in reverse. So the first thing I want to do here is go ahead and sketch some kind of an ellipse here. I wonder if I can do shapes on here. I actually don't even know that. Probably not something to mess with right now, but so I'm going to sketch an ellipse. That was not horrible. It wasn't great, but it wasn't horrible. So our ellipse, we're going to say that it goes out A units in that direction and B units in that direction. So we want to parameterize this one. Parameterize. So we want to parameterize an ellipse. It's generally the same idea as a circle. So again, the idea is, because it's kind of circular in nature, we're going to use polar coordinates to do this. Well, let's see, x is going to have to be some kind of a cosine of t. But in order for us to get this, so the radius in the x direction, the biggest that x can ever be is a units out. So if I were simply to plug in 0 for t, and here we know that y is going to be some kind of a sine of t. It might make it easier to see this. If I were to plug in 0 for t, cosine of 0 is 1. So what would I have to multiply times 1 to get that a right here would be a. And then, of course, sine of 0 is 0, so that wouldn't make any difference. If we go to pi halves now, which is where that b is, cosine of pi halves is 0, so that part goes away for x, but the sine of pi halves is 1, so what would I have to multiply by 1 to get its maximum value right here, which is b, so that's b. And I don't know if you remember this or not, but if you were to take and divide the x equals a cosine t on both sides by a, you would get x over a equals cosine t. And then if you divide the y part by b, you would get y over b equals sine t. And then if I were to take and I were to square both sides of each one of those equations, what you would end up with is x squared, what you would end up with is x squared over a squared for the left one, and then you would have y squared over b squared for the second one. And if you were to take and square cosine squared plus sine squared and add those together, which is this x squared over a squared plus y squared over b squared that equals 1. This right here is the general form of an ellipse where in the x direction your maximum values are a, and in the y direction your maximum value is b. So that just gives you your intercepts. Anyway, so in this case we're going to use those because we're going to do our line integral of 1/2, or 1/2 of the line integral of x dy minus y dx. So let's see, we're going to have 1/2. Once again, this thing is going to go all the way around from 0 to 2 pi. We already checked to see that it transverses the correct direction, which it does. So 0 to 2 pi. X was a cosine of t. dy is going to be b cosine t. Oops, b cosine t dt, but I'll add the dt at the end because it's going to be dt for both of them. And then minus y, which is b sine t, times dx, which is the derivative of x. That's going to be negative a sine t. And then, like I said, I can pull the dt for both of them out here. So it looks like what we have in common is I've got an a and a b in common in both, and those are just constants, so I can pull both of those out to the front. So I'm going to be able to pull an ab out to the front, which is going to leave us with cosine squared t minus sine squared t dt. Oh, not minus. What am I talking about? It's minus minus, which is plus. That makes this even nicer. Cosine squared plus sine squared. So all we're going to get then is ab over 2 times the integral from 0 to 2 pi of 1 dt. So we're going to get ab over 2 times t from 0 to 2 pi. Plugging in 2 pi, you're going to get ab. Plugging in 0, we get nothing. I'm sorry, ab pi. Plugging in 0, you get nothing. So the area of your ellipse is a times b times pi. And something even cooler, if you think about it, at least it's cool to me, let's do this in red because I think it's awesome, is that what if a equals b? Doesn't really matter which way you do it, but if a equals b, that means the distance from the origin is exactly the same all the way around, which means that you would get a squared pi, or pi r squared. So it's just a circle, if a and b are the same. Anyway, pretty cool.